Today, we're going to create an animated water surface using vertex displacement. Let's go. Alright, so we're continuing our series on vertex animation, and today we're going to do some animation with our vertices using something called a Gerstner wave. And that's a math formula that we use to simulate the movement of waves. So let's go ahead and get started. We're going to create this simple shader called water animation, and I'm just going to apply this to my plane. And the first thing that we need to mention here is that I have a plane that I've created. I created mine in 3ds Max, but you can create yours wherever you want, Blender maybe. And you can see that the important thing here is that we just have it subdivided quite a bit so that there are enough vertices for us to animate. If you use the default plane, it just comes with, like it's very sparsely tessellated, or it doesn't have a lot of triangles. And so you need to use a plane that has plenty of triangles like this one, so that you're able to see the animation that we're going to create. All right, let's go ahead and open up our shader here, and we'll get started. All right, so we'll start out with a blank slate here. We have an empty shader, and I've just created a lit shader. The first thing that we're going to do is add a couple of parameters. So I will add a vector3 parameter, and I'm going to call this wave direction. And for our wave direction, I'm going to give it a default value of 100. So we're just going to have our waves default to moving in the x direction. I'm going to add another parameter here called wavelength. And this will control the distance between the peaks of our waves. And for the default wavelength, I'm just going to give this a value of 4.5 meters for now. The next one we're going to add is called wave height. And for wave height, I'm going to give this a default value of 0.2. And then there's one more parameter we're going to add here, but I'm going to save that one for later. We'll add it in just a minute. All right, so the first thing that we want to do is we're going to set up a math formula called a Gerstner wave. And what we're going to do is introduce the time or the movement of our vertices. And then we're going to add the actual vertices to move them around with the Gerstner math. So let's start out with the speed or the time of the movement of our vertices. So the first thing that I need is a constant, and what we need is 2 pi, and 2 pi is called tau, so I'm going to bring in the constant tau. This is like 6.28 something something, and we're going to divide 2 pi by our wavelength. So I'm going to bring in my wavelength parameter here and divide that, and divide tau by that. Then, to control the speed, we need to introduce the gravitational constant. And on Earth, gravity moves at 9.8 meters per second. And so we're going to multiply by 9.8. Now, obviously, if you're creating liquid on another planet, you would change your gravity here. But for the most part, we're just going to be dealing with earthly water. So we're going to leave that at 9.8. Then we need to take the square root of that gravitational constant, and then finally we're going to multiply by time. And this little math formula here will help us to control the speed that our vertices are moving. So I'm just going to move that right over here. The next thing that we need to do is bring in the position of our vertices. So we're going to bring in the vertex positions in object space. And then we need the wave direction. Now remember, we defaulted this to 100, so our waves are moving in the x direction. And because this is something that users can control, we're going to add in a normalize because we always want our wave direction to be a value of 1. And now we're going to multiply this direction by our wavelength, or tau divided by our wavelength here. So I'm going to connect up these nodes. Then we're going to do a dot product between our position and our wave direction here. And then we're going to bring in our speed value here. We're going to subtract our speed from our position value that we calculated here. And now, I bet you knew this was coming. All waves use sine or cosine, so I'm going to add a cosine value here. And we're going to wire that in. Then we're going to multiply by a value that will filter out our x and our z values. I'm just going to set those to 0. And for our y value, I'm going to set it to 1. So what this is doing is making it so that our vertices are just moving up and down. We multiply the x and the z by 0. We multiply by the y by 1. So we're just keeping the y and setting the others to 0. And then finally, we need to multiply this whole thing by our wave height parameter. So we'll bring in our wave height parameter and multiply by that. And now, with all of this done, this is how much our vertices are being offset. So we need to add in our vertex position here in object space and just add it to the offset amount that we're doing here. So this is the core of our Gersner wave formula. This is how fast our vertices are moving, and then this is how they're moving here. I'm just going to make a group here, and we're going to call this speed, just to kind of isolate these nodes. And then, yeah, now I think what we can do is take this and plug it into our position on our master stack here so that we can animate the position of our vertices. All right, let's save this, and we'll jump back over to our scene and take a look at how things are coming along. Okay, cool. So you can see that we've got the initial bit of our animation going on here. We have our waves proceeding along here in the y direction, and we've got a wavelength of 4.5 meters and a wave height. I think I said it was like 0.2 meters, something like that. So our waves aren't too tall. All right, there are a couple of things that we can do to improve this. First of all, this is only one wave, and we're going to get to making multiple waves in a minute. But one thing that I'm noticing here is that if we look at water, water often has peaks that are sharp. And so we can add a bit to our math formula. Right now, our waves are perfectly smooth, and we need to add a little bit of a sharpness so they come to a peak before they go back into the valley again. Right now, the peaks of our waves are completely smooth. So let's go ahead and add a little bit more math so that we can sharpen the peaks of our waves. So we'll come back here to our shader, and let's grab our wave height. We're going to use that for sharpness. And we're going to multiply our height by our wavelength, by our 2 pi divided by our wavelength. We're going to multiply that by our height. So I'll bring it down here and create a multiply and wire that in. Then we're going to add another value here, and this is another parameter that we're going to call sharpness. All right. And just for now, we're going to default this value to 1 so that it's kind of accentuated so you can see how sharp things are. But I'm going to take our peak sharpness value and drag that in. And we're going to divide our peak sharpness by our wave height value that we've calculated here. And then we're going to multiply this again by our wave height. So we'll connect that up. And now, right up here where we've done our cosine, I'm going to drag down, and instead of cosine, to calculate sharpness, we actually need a sine value. So I'm going to bring in sine, and I'm going to multiply sine with the result that we've calculated previously. Just wire that right in, just like that. And now we need to multiply by our normalized wave direction. All right, so there is the math formula that's going to give us our sharpness. So here at the end, before we add in our final position, we can subtract out the value that we've calculated for our sharpness. And this is going to allow us to get waves that are peaked. So I'll connect that up and we'll hit save. Now I'm just going to select these nodes here and group them together. And I'm going to call this our sharpness, just so we can kind of keep things organized. All right, let's save that and take a look at our result. Yeah, now you can see that we've got these nice sharp peaks, and then we've got these troughs in between. Now, if we want to tone these down and make them a little bit more realistic, because most water is not quite that sharp. This is like as sharp as it gets, like the most extreme. So let's go back and we'll set our peak sharpness to default to a value of something like 0.3. And then take a look again. And now we've got some waves that are, you can see how they're a little bit sharper than they were before, but not like razor sharp as we just had them. All right, cool. Now there's one last thing that we need to add to our Gerstner wave formula. Right now we are controlling the position and offset of our vertices, but we're not actually controlling the normal. And so if you look at the reflection here, it's reflecting as if our plane is still facing straight up, when in reality, we do have these waves, and we want to calculate the derivatives of our normals so that we can offset our normals and make them face the appropriate direction. So let's do that right here at the end, and then I'll show you how to add in multiple waves. All right, so we're going to kind of come down here to calculate our normal, and we're going to use both the sine and the cosine to calculate our normal. So I'm going to grab our sine node here and drag down and add a multiply. So the first thing that we're going to do, we're calculating our normal in tangent space. And so the first thing that we're going to do is calculate the x and the y components, and then I'll show you how to calculate the z component. So we're starting out with our sine. I've got our multiply here, and we're going to grab our wave height value and drag that into our multiply. And then we're going to multiply that by our wave direction value that we've got up here. And then we're going to split this. This is our x and our z value. So let me add a combine node here. So this math that we've done here is the x and z of our normal. So I'm just going to wire in x and z. And now we need to calculate the y. So in order to do that, we need to do something very similar, but instead of using sine, we're going to grab our cosine. So here's our cosine node up here. I'm just going to drag down and add a multiply. And we'll also multiply that by our wave height value here. And then we'll multiply that by our peak sharpness value there. And then the last thing that we need to do to this value is invert it. So we'll add a 1 minus, and then we'll wire this into our g component, or y, of our normal. All right, so here we've computed the x and z, and here we've computed the y of the normal, and then we can plug this directly into the object space normal output of our normal. So I'm just going to select this and group it together, and we'll call this our normal. All right, so here we're calculating our speed, our sharpness, our normal, and this is our position offsets, and oops, I misspelled that, and there's our normal. All right, so let's save this and take a look at what we get. Okay, now you can see, now that we're offsetting our normal, our reflections are really warped, and that's exactly what we want. We want the reflections to be coming from normals that are actually facing the direction that they would be if our vertices are displaced like this. You can see that we're getting some nice deformation here on our positions, on the positions of our vertices, as well as the normals of our vertices. All right, so that is how you create a Gerstner wave for water. Now the next thing that we need to do is combine multiples of these waves together. Right now, our pattern is just kind of really repetitive, But if we combine multiples of these together, what we're going to get is a bunch of different Gerstner waves going in different directions and different heights. And it's going to make our values look a lot more organic looking. One of the main things that we do in shaders is try to break things up so they're not repetitive. We do that with texture tiling, and we also do that with Gerstner waves. So let's go ahead and do that. All right, so what I've done here is I've created a new subgraph node that's called Gerstner wave. And this is doing exactly the same thing as this shader that we just created. I just took all of these nodes and pasted them into a subgraph. And here are the exposed parameters that we had. And then our outputs for our subgraph are here. So you can see I created an offset value. It's a vector 3, and I created a normal value that's also vector 3. So I'm outputting my offset and my normal from this subgraph. Now, if we come here to our water animation, I can find my Gerstner wave subgraph here and drag it in. Now you can see I've got this subgraph that does exactly the same thing as all of these nodes. So if I just take all these new nodes here and scoot them over, and we're going to put in our subgraph instead. I'll just drag in my offset value and my normal value there. And now you can see I've got my values set to X, 4.5, 0.2, and a peak sharpness of 0.3. And then actually, the last thing that we need to do before we offset our values, these are offset values. They're not actually absolute values. And so I need to add in my position node, the position in object space. And we'll just add that to our offset values and then pass that into our vertex position. Okay, so we'll save that, come back to our scene. And now you can see we've got the exact same thing. So I've made all of these nodes here into a subgraph. And so I can take these nodes that we just created and delete them and just use this subgraph as it is. Now the cool thing about having this Gerstner wave as a subgraph is I can take this subgraph and copy and paste it to create multiple Gerstner waves. And each of these waves I can change the values around just a little bit. This first one I'm going to set to negative 0.2 and negative 0.7. This next one I can set to negative 1. This next one I can set to negative 0.5 and 0.5. So you can see all my waves are now traveling in different directions. And I can also change the wavelength. So this first one I'm going to make kind of short, 2.5. This one I'll set to 3. And then this one I'll set to 1.8. And let's change up the wave heights as well. We're going to make this one a really short one, 0.07. We're going to set this one to 0.05. And this one to 0.04. And then for sharpness, 0.3, 0.3, and maybe just a little bit different, 0.4. Now for the offsets, I can add all these offsets together. And then we'll add them to our object space position. And then for the normals, we're just going to add the normals together as well. So we'll add our normals together and pass those into our master stack normal slot. All right, let's go ahead and save this. So we've got 3 Gerstner waves going on here that are calculating our vertex offsets and also our vertex normals. And now, we've got some really nice looking water. And if I select our plane here, you can see we're creating some fairly complex vertex animation here with our 3 different Gerstner waves added together. Now if we move our plane down here, we can put our water just in the moat here around our central pedestal. and create some pretty neat looking animated water surface for our object. Now, obviously, there are a lot more appearance properties of water than just animating the surface. You know, we've got refraction that we need reflection, we need maybe foam, maybe some smaller ripples on the surface. And all of those things are going to be things that we cover in future videos. So be sure to subscribe if you want to see what we're going to do in the future to animate this water. All right, so we've got our Gerstner waves going on here, and in future videos, in the next couple of weeks, we're going to add depth. We're going to add little surface ripples. We maybe even add foam to our water, all kinds of things to make our water look more realistic. But for now, we've got some pretty realistic looking animated surface ripples with our combination of our 3 different Gerstner waves. All right, let's switch over to Unreal, and I'll show you how to do the same thing there. All right, here we are in Unreal, and you can see, just like we did in Unity, we've created this nice animated water surface with our shader that is creating the animated vertices using the Gerstner wave formula. If we switch our viewport setting here from lit to wireframe, you can see that I've got this wireframe plane that is subdivided quite a bit, or it's tessellated a lot, so there are a lot of vertices. And as I said before, the reason to do this is so that you have enough vertices to move around so that you get a nice realistic looking water surface. So let's take a look at how this shader is set up. So the first thing that we're going to do is take a look at one Gerstner wave, because we actually got 3 waves going here. We're just going to take a look at one, and I'll show you how that's created. And then I'll show you how to combine the 3 together to make what we've got here. All right, so here is the shader we're creating today. I'll just come over here to the speed section and zoom in, and we'll go over this. So we've got our pi value here, 3.14, etc., etc. And we're doing 2 pi. Now, in Unity, there's a value called tau that you can use for this. But in Unreal, you just give pi a multiplier value of 2, which will give you tau. All right, so then we're going to divide our 2 pi value by our wavelength scalar value here. Now, notice this is an input here because we're working in a material function. And the reason that I've set this up as a material function instead of a material is because we're going to be taking everything that's happening here and repeating it 3 times. So we want to create a material function here to build our Gerstner wave in instead of a material so that we can repeat it. All right, let's get back to the speed value here. So we're going to divide tau by our wavelength input, and then we're going to multiply that by a value of 980. Now remember that Unreal is using units in centimeters, and so this is 980 centimeters per second, which is our gravitational constant, 9.8 meters per second, or in centimeters, 980 centimeters. All right, so then we're going to take the square root of that and multiply by time, and that controls the speed of our vertices as we're moving them around. All right, the next thing that we're going to do is take the absolute world position. Now, notice that it says excluding material offsets. If I bring in our settings over here, there are a bunch of different settings you can use for world position. And we're using the one that's excluding material offsets because we want to do this before our material animation. What we're actually doing here is animating the material. So we need to grab the world position before the material is animated. All right, then we have a vector 3 input here, which we've defaulted to 1, 1, 0, 0, 0. And we're normalizing that. And then we take the dot product of that. Oh, and then we multiply it by our 2 pi divided by our length. And we dot product that by our world position. And then we subtract our speed. And we take the cosine. And we multiply it by 0, 0, 1 because we only want the Z offset. And then finally, we multiply that by our wave height. And that gives us the vertex position offset. So that part of the shader is the most basic part. This plus these two multiplies here. Now to take it a little bit farther, we can add in this steepness function down here, which is going to make our waves look a little bit more peaked. So we'll take our input wave height and we're going to multiply that by, so our wave steepness here divided by a multiplication of our wave height and our 2 pi divided by our wave length. All right, and then we're going to multiply that by the sine value here. So previously we created the cosine, now we've got our sine coming down, and we're going to multiply that by our steepness. And finally our steepness value is going to get multiplied here by our normalized input direction. Then we'll take our steepness and subtract it from the position that we've created before, and that's going to create our final offset value. All right, so that portion of the shader is creating the position offsets. And the other thing that we need to do is recalculate the normal, because when we move our vertices around, we actually need to update the normal so they're not continuing to just point straight up. So to create our derivatives for our normal, we're going to take our sine value here and we're going to multiply that by this value down here from our steepness. And then we're going to multiply that by our normalized direction. And we're going to filter out just the red and the green. That's our x and our y component for our normal. Then for our z component, we're going to take the cosine here and multiply that by our value down here from our steepness. So we're going to multiply our cosine value by that. Then we're going to multiply it by this divide here, giving us the steepness. And we're going to invert that, so we're going to use a 1 minus node. Then we're going to append these together. So this is going to give us our z value. This is going to give us our x and our y value. And we're going to normalize the result and then output our normal. So our material function here is giving us both our vertex offset and our normal. So if we take this material function here, this is our water Gerstner wave function. Now we're going to add this into our material. So here's our final material. And you can see here that we have 3 copies of our water Gerstner wave. So there's number 1, number 2, and number 3. And you can see that they each have wavelength, wave steepness, wave height, and direction. So what we're doing here is creating 3 different copies of our wave with different input parameters. So here are the parameters that we've created. You can see this one has a wavelength of 2.5 meters, 3 meters, and 1.8 meters. And each of them has a steepness value of 0.3, although this one has a 0.4. And then for a height, we have 2 meters, 1.4 meters, and 1.2 meters. So these are all slightly different, and they also have different directions over here. You can see this one's moving in the x direction, but this one's kind of moving in a negative diagonal direction, and this one is on a separate diagonal. Then we take the vertex offsets coming out of each of these, and we add them together. So here we've added together the offset from the first one with the second one, and then we've added the results of that to the offsets of the third one, and passed that into our world position offset. Then for our normals, you can see that our normals are coming out of here, and we're using this node here called blend angle corrected normals. We've got our base normal and our additional normal coming in from our second Gerstner wave node. And then we're taking the result of that and doing it again with our third, and then passing that into our normal output. So that's how we create our animated vertices for our water. We just have our 3 Gerstner waves combined together to give us our final result, which ends up looking something like this. All right, now a long time ago, maybe 3 years ago, I created this tutorial where I showed everybody how to create water. And this Gerstner wave bit of it was just one part, but we also had depth, and we had surface ripples, and we had foam, and a bunch of other things. And so in the next couple of weeks, I'm going to show you how to do those things again. But this time we're adding in Unity, so we're showing how to do all of these water techniques in both Unreal and Unity. All right, so stay tuned in the next couple of weeks. I'm going to show you how to add all the extra bells and whistles to our water so that we've got nice looking water, not just with vertex displacement, but with surface ripples and depth and refraction and all that good stuff. So come back next week, and in the meantime, have a great week, everybody.